Today I'm going to briefly introduce our work in estimating the time of sudden shift in the location or scale of ergodic-stationary process in the statistical process monitoring application. And this paper is collaborated with my PhD academic advisor, Dr. Marcus Perry. So firstly, let's introduce our motivation for this project. Recent advances in the data acquisition and storage technologies has permitted data to be sampled at a high rate. For example, if you take your sample, use sensors at 100 hertz, that means you can get 100 samples per second. And this number can be even larger. However, the proximity of these samples can easily introduce the autocorrelation into your observed data. And also modern data rarely follow normal distribution. So making the use of traditional estimators that has unrealistic assumption questionable. And also the lack of a suitable change point estimation method in case of the autocorrelation is a very important gap in the statistical process control literature that we want to fill in. And here we have a couple of examples that those are all very wide used change point estimator, but each of them has its limitations. So in this project, we focus on estimating the time of step change in the ergodic-stationary sequence, and this is the definition of that types of time series sequence. So for time series Y1 and Y2, it is ergodic-stationary if the covariance of YT and YT minus 1 depends on S, and if S goes to infinity, this covariance value goes to 0. And it's important to have an accurate and reliable change point estimator because it can help you in the post-signal diagnostic of using a control chart to monitoring. And we introduced many requirements of modern data and the limitations. Before we can use change point estimator, we need to select appropriate control chart to use. And this paper, a distribution-free joint monitoring scheme for location scale using individual observations. This is one control chart we developed. And this control chart can take the observation into consideration and also circumvents the model misspecification problem. You don't need to specify normal distribution to use this control chart. And let's briefly take a look at this control chart. We first define the strategy of clipping. So for a time series like YT, what is clipping? So we can clip the time series at the median to get the clipped binary sequence CM. So CM equals to 1 if YT is greater than the median, and it equals to 0 otherwise. We can also clip at the IQR to get the binary sequence CIQR. As you can imagine, the CM is representative of the location of your original time series YT, and the CIQR can be represent your scale of your original time series YT. And after that, we can develop the joint mass function for this clipped binary process, use the Bahadur approximation, and then use the SPRT with that is widely used when you develop a Q-sum control chart. Q-sum is cumulative summation control chart, and this huge equation is our control chart. That LT is the charting statistics, and if you are design this chart to monitor increase in your mean, then you use the first formula. If you design this chart to detect a decrease in the mean, you use the second row of equation. The CT there is simply the observed value of that binary sequence. And you have the term eta t there that takes the autocorrelation into consideration. And next, we can take a look at the methodology of the change point estimator itself. If we consider this binary sequence, that we mentioned before that we get through the clipping. And we can denote the tau as this that unknown change point that we want to estimate. We can have the first one is the built-in point estimator of the Q-sum control chart that is developed by Page. This one is simply defined as the most recent time index yielding a cumulative sum of 0. So if you look at this plot, right, you have a signal of that chart at the sample 114, but the time you have the charting statistic equals to 0 is 98. So the 98 would be your built-in Q-sum estimator of the change point. And we then also developed the maximum likelihood estimator by ourselves. And yeah, this here shows the likelihood function and also the likelihood function estimator for that change point. But we here only list the result for the first order dependence case because this is very easily extended to higher dependence order. And the note here, we don't have some explicit formula to estimate that one, but we have higher computing capacity nowadays, so we can use analytically, so numerically solve for these estimators. And the next section is the performance and the recommendation. We use the Monte Carlo simulation to compare the relative performance between 3 different change point estimators. The first one is the Q-sum built-in estimator. The second one is what we proposed, is the maximum likelihood estimator. And the third one is the Perry and the P-nautilus change point estimator. And here is explains how we do the simulation. For the in-control process, we first, because we only consider the first order dependence, so we first simulate our in-control process from an AR1 model. For the length of M and the autocorrelation parameter is 5. We also investigate the robustness of these 3 change point estimators. So we change the distribution of the arrow to assess it. And we have the in-control level parameter delta there. And also finally, we have that curvature of that arrow distribution. After we simulate that in-control process, we can estimate the quartiles and get the clipped binary sequences. And then we can estimate the correlation parameter and put in our control chart. And directly from this in-control process, and based on the maximum likelihood, we can develop also the change, the Perry and the P-nautilus estimator. After the in-control process, we have the monitoring begin at the M+1, the time M+1, and we then simulate a change in the location at time tau. So M+tau+1 is the first observation in that out of control process, and we keep monitoring this process until we get a genuine signal from our control chart at time M+t. And here are those performance. We summarize the performance using the empirical CDF here. The different beta here is different change of scale, like how much of the change you have in your location. And also we change the skewness to check the robustness. As you can see, both Q-sum built-in estimator and our proposed MLE is robust to the skewness, better than that the plot in the panel C. And also our proposed MLE outperformed the Q-sum estimator in the estimating the change point tau at equals to 50. And finally, we have an illustrative example. Yeah, so here, this example is just simply detect the hotspot occurrence in a laser powder bed fusion process. You can see Z process at the Z point Z there is some hotspots, and we want to detect it as quick as possible. And this is a very well-known data set in the statistical process control. And we know that the change occurs at the time 100. This is what it looks like for our Q-sum control chart applied on the time series of that laser melting data frame. And here are the results for the Q-sum control, Q-sum built-in estimator and our proposed MLE. You can see our results can estimate the change point better because the change point is really 100 and our estimate is 94 for the location change and scale change is 99. And what Q-sum control chart estimate is 84 and 99. Yeah, that's all. Thank you.
Thank you.